Okay, hi everyone. So this is lesson 1 of continuous probability distributions, our last unit, unit 6. So the first part of this lesson is just reading. So I'm just going to read through some of this. We're comparing the discrete probability distribution to the continuous probability distribution. And discrete was what we did in unit 5. And continuous is what we're doing in unit 6. So discrete random variables mean that the random variable x can only take on clearly defined separated values obtained by counting whole numbers, 1, 2, 3. And the discrete probability distribution is a list of all of the discrete values that the random variable can assume, as well as their probabilities, all of the outcomes as well as all of their probabilities. Examples of discrete are number of newspapers sold per day from a corner box and the number of vehicles driving into a particular service station. Only whole numbers make sense for those. Now for continuous, our next unit, unit 6, they're associated with measurements that can be made to a desired degree of precision, such as length, height, weight, or speed. Examples of it could be time. It takes for downhill skiers to finish the course measured in 1/100th of a second, or the distance in long jump measured into the nearest centimeter. When we have continuous distributions, we have different types of continuous distributions. So we have a symmetric distribution here, a positively skewed distribution here, which is also the same thing as right skewed. We have a negative distribution or left skewed. And then we have bimodal over here. So there's some different types of continuous distributions there. And the two that we're doing in this first lesson are called uniform and exponential. So here are our key concepts about continuous probability distributions. Right? The random variable is a variable whose value in the experiment is determined by chance alone. The continuous random variable is one that can assume infinite number of values. That's why it's a measurement. A discrete random variable only takes on distinct values. Okay, that was unit 5. A probability distribution can be either continuous or discrete, depending on the nature of random variable. The probability of a random variable defines the probability of occurrence of every possible value that the random variable can assume. The probabilities making up the probability distribution are between 0 and 1. Zero and 1, and their sum must equal 1. A probability distribution can be presented in the form of an equation, table, or graph. So last unit, in unit 5, mostly we used equations. We sometimes organized them into tables, these probability distributions. But for this unit, it's going to be all about the graph. And that's even starting with this first lesson on uniform distribution. So let's get into that. Modeling distributions with equations. Often we want to find the probability that a variable falls within a particular range of values. This kind of probability can be determined from the area under the distribution curve. So probabilities are going to be taken from areas underneath the curves of these continuous data sets or scenarios. The curve itself represents the probability density, the probability per unit of continuous random variable. Many distributions can be modeled with equations that allow the areas to be calculated rather than estimated. So the first one we look at with these curves is the uniform distribution. It's the simplest of all of them because all possibilities are equally likely. So our example is the driving time between Toronto and North Bay is found to range evenly between 195 minutes to 240 minutes. And so the question is, what is the probability that the drive will take less than 210 minutes? So things we have to notice are that the time distribution is uniform because it says this word evenly. This means that every time in the range is equally likely. The graph of the distribution will be a horizontal line and the total area under this line must equal 1. So these little italicized bullets are just ideas that are going to help us to create the probability distribution as a graph. So that's what we're going to do first. I'm just going to move this down slightly. We're going to move and draw a graph. Let me just make this a little thinner. Graph it. So my graph, just like probability distributions in Unit 5, we did them just briefly in the first lesson. The probability goes on the y-axis, and the unit of the outcome, which is time in this case, goes on the x-axis. And so the question read that the time it takes to go from Toronto to North Bay is somewhere between 195 to 240. So every single time in between, like it'll take a certain likelihood to make it from Toronto to North Bay in 195 minutes. It'll take that, it's exactly the same likelihood because it ranges evenly, it's uniform. That likelihood of it taking 240 minutes is also going to be the exact same probability. We don't know that probability. But every single time, like 200 or 215, they're all going to be at that exact same likelihood of occurrence, which is my question mark here. And so that's why the graph of this probability distribution is a horizontal line. Okay. And the thing about that it ranges evenly between 195 and 240 is that we can figure out what the probability is of that horizontal line is by considering that the area underneath the curve is equal to 1, right? 100% of the travel times is between 195 and 240. So the area underneath this curve, it's going to be something in between here 100% of the time. And we should recognize that this this graph is really creating then a square because we want this side here. I'm going to go the difference between these two numbers, 240 minus 195. That's 45. So the difference here is 45. So that would mean that because this is a square or a rectangle, we're not sure even, this over here, the area has to be equal to 1. I'm going to call this side the width. So this is 45. No, I'm calling this the length side. The width, we don't know what it is. Right? So it's like saying 45W equals 1. So I'm going to divide both sides by 45, and I get that my width is the probability of 1 over 45. And that's what this question mark is equal to. That's what that question mark is equal to. So that's the entire probability distribution. The next step I'm going to do is to answer the question. So the question reads that instead of, or they want the likelihood of it being less than 210. So originally it was 195, and now we want it to go to 210. This is like a smaller slice of that square. We know that the heights are still going to be the same, 1 over 45. But now this width has changed. So I'm going to take the difference here, right? And that's 15. So that's the width. The area is still equal to length times width. And we know that our length is 1 out of 45 and our width is 15. And so when I multiply this across, I get 1 out of 3, right? It's a 33% chance that the drive will be less than 210 minutes because the area underneath the curve is the likelihood or the probability of that happening. Okay, so there's a 33% chance drive taking less than 210 minutes. Okay. Right, and if we wanted to, we could have used the same graph and just like used a different color or something. I'm just going to add to that over here, like 210 would be here. Its likelihood is up here, and this is that smaller rectangle that is the same one over here. Okay, so this is our adjusted graph. Right, the first one was to figure out the entire probability distribution. The second one is to answer the specific question that they're asking. Okay, so that's uniform distribution. The next one that we're going to look at, and the last one for this lesson, is the exponential distribution. This one is going to use formulas again. So we've got the exponential distribution when it comes to continuous data sets. They're going to be used to predict waiting times, okay, between consecutive events in any random sequence of events. The equation is this. You've got to use a special button on your calculator called Euler's number. It's going to look like something like that, potentially, on your calculator. And it's going to take Euler's number and raise it to an exponent that we want. And that exponent is going to come from the product of k and x, right? X still being our random variable x. Okay, so here are the two formulas that we're going to use. And it says right here, recall mu is population mean and x bar is the sample mean. So we're using the population mean. Whatever mean they give us, we're going to stick in there. So note, the longer the average wait time, the smaller the value of k, and the more gradually the graph slopes downwards. The exponential distribution is not symmetric, and its mode is always 0. So the longer the waiting time, the less likely it is to happen. And when we use this formula, we're going to be losing a bit of precision because the formula is really finding the area underneath each time interval. So here's our example. The average time between phone calls to a company switchboard is mu equals 2 minutes. That's our population mean. Calculate the probability that the time between 2 consecutive calls is less than 3 minutes. So for our answer, we're going to have to create a chart just like below, because the exponential distribution is continuous and deals with data values over a given interval. So we've got our intervals created here. We want less than 3 minutes. So actually, if it's less than 3 minutes, we don't need this final column. I should say row, sorry, row. Because we should know from our histograms with these brackets that square bracket means including. So the 3 is including, the 2 is not in this case, and we want less than 3. So this third row is good enough for us. So when we do exponential distributions, we're going to be grouping each major whole number into an interval and then using its midpoint to substitute into our formula. So The midpoint here, x, is 0.5, and I'm going to color code this a little bit. I'll start with the purple color here. You know, one thing we have to do is figure out what k is. It does look like k is 0.5, but I'll do that first just on the side here, right? K is equal to 1 over mu, and they said that mu was 2. So it's 1 over 2, which is, I'm just going to use the 0.5. That's the 0.5 that they put in right here, in here. Okay, so in our first section, the likelihood that random variable x is less than 0.5 is going to be equal to 0.5 Euler's numbers raised to the negative 0.5 times 0.5, the x, right? The x is the midpoint here, and that was the midpoint of the interval. So we're going to be careful using our calculators. We're going to multiply in the exponents first to get a negative 0.25. Then we're going to evaluate Euler's number and try and keep all the decimals if you can. So making sure you know how to use that button for Euler's number. I'm just going to write it to around to 4 decimal places there, but I'm leaving it really in my calculator. So my answer for that first case is 0.39. That's going to be our likelihood of being in that particular interval from 0 to 1 minute. Now I'm just going to change colors, and I'm going to go with orange here. So for my second section here, I'm going to be saying that the random variable x is less than the midpoint of 1.5. I'm going to be substituting in, can I change that here? Yeah. I'm going to be saying 0.5 times Euler's number to the negative 0.5 times 1.5. And my next line with my stacked equal signs, my multiplication of negative 0.5 and 1.5 is negative 0.75. I evaluate that Euler's number first. When I do that, I get 0.4724. And then I multiply that by 5 to get 0.24. Okay, so that is my second case's likelihood. And then my final likelihood, I'll do that in this lighter blue color. I think I'm just going to squeeze it down here. Oh no, maybe here, 3. Right, I'm subbing in 2.5, so that's the likelihood that random variable x is less than 2.5 as the x, is 0.5 to the Euler's number times negative 0.5 times, oops, there we go, times 2.5. Okay, so then when I multiply the negative 0.5 times 2.5, I get negative 1.25. And then I'm going to evaluate Euler's number. That's going to become 0.2865. And then when I multiply it by that k value of 0.5, I get 0.14. So 0.14 goes over here into my chart. And so now the chart just helps me organize it. And I'm trying to come up with the likelihood of being less than 3 minutes. So it's the first case or the second case or the third case, right? That keyword or, this is coming from even our very first probability unit, the additive principle. When we think of the word or, we have different cases that satisfy the overall event case. We've got to add up those probabilities. So the last thing I'm going to do to get my answer is just say the likelihood, I'll change colors, final answer, the likelihood that random variable x is going to be less than 3 minutes is going to be adding up those 3 cases. And my answer is then 0.77. So it's a 77% chance of waiting less than 3 minutes. Less than 3 minutes. Okay, that's it for our lesson today. And now you guys are ready to do the homework for this section. Thank you for listening.